Okay, so we'll continue on here. I want to I guess give you just a couple of housekeeping things. First, I've decided to extend the due date for homework 5 to May 31st. Okay, so it was originally due on Friday, and I'll give everyone 3 extra days. We'll make it due Monday, May 31. That's Memorial Day. And so if you want to kind of take your time over the weekend to kind of work on it, that's as well. That's fine. Some people had questions about how the poker card ranking things work and stuff like that. The short of it is each hand should basically just have one ranking. So you kind of want to you'll want to kind of check, and so if a hand has 4 of a kind, somebody could say, does that also have 3 of a kind? Does that also have 2 pair or a pair, or things like that? So the answer is no. It's only going to have 4 of a kind. So if it's 4 of a kind, it should only have 4 of a kind, and it should not count as being as having a pair. So when you check for does my hand have a pair, you should check to, it's fine to just make sure to see if there's, the number of cards that have a certain rank is, 2 or more or something like that. But you should also make sure that it doesn't, that it's not also a 4 of a kind or something like that. Okay. So yeah, each hand should only have 1 label. That's the answer. Okay. So if it's like a full house, which has both 3 of a kind and a pair, it should only show up as being a full house. It should not show up also as being 3 of a kind. It should not also show up as having a pair or 2 pair, things like that. So yeah, each hand should only have 1 label. Okay. It says classify in the instructions, it says classify function returns a list with all its classifications. Yet, I apologize. So the right, it should just be 1 entry, and I think this will be slightly different from the textbook solutions. So there are like if you search around on the internet, you can probably find like solutions to the textbook and stuff like that. So this method where we're going to just do kind of just 1 hand rather than one ranking, rather than like an assortment of things, that could end up confusing. So it might end up being slightly different. But I think the numbers should still work out. I don't know. Are there any other questions there? And then also the homework will be due on Monday, and then I've assigned data camp homework, where I think I just said earn 1,000 XP. So just do some chapter on data camp there. And then I think I was going to have a homework assignment related to sklearn, and I think I will just cancel homework 6. So we'll just finish homework 5, and that will be good enough, if that's okay. All right. So we'll do that, and then I'll go over kind of a little bit more details regarding the final exam. The final exam will take place on the day of our scheduled final, and then I'll provide more details on how that will work. So it will probably be more focused on pandas and matplotlib, and maybe some Python function writing. So it's going to be, I don't know if I can write a final exam that will encompass the entire course, where it's like you can still complete it within a certain amount of time. So I just kind of have to think like what kind of problems I can give within a certain time frame. And so anyway, working on that, I'll give you guys more details. Okay. All right. Let's go ahead and take a look at the notebook I have today. Okay. So I was going to do another example with sklearn, and we will look at a classification problem, and so we'll take a look at that. Okay. And again, sklearn is just kind of the big library that that we use in Python for almost all kinds of machine learning tasks. All right. And so the first thing I'm going to do is I'm going to import the iris data set. Okay, so the iris data set is a very, very popular data set. Okay, the iris flower data set even has its own Wikipedia entry. Okay, and these are 4 numeric variables. Okay, so we're looking at irises, and there are petals and sepals. Okay, and so this part down here is the petal, and this part up here is the sepal. Let me see. Okay, that is not. So you have, oh, I'm sorry. The big parts are the sepals, and then the little parts up here are the petals. Okay, I apologize. So when you look at an iris, they have the sepal and the petal. When you look at kind of these things, so it's kind of like these things. So this would be the iris, and so anyway, this was used by Ron Fisher, and it was Anderson's iris data set, because Edgar Anderson kind of went out and collected this, looked at 3 different species of iris. Apparently there's many species of iris, and measured, the width of the petals, the length of the petals, the width of the sepals, and the length of the sepals. Okay. And so this is what we have. We're measuring these parts of the iris, and it's loaded up here, and it's very popular among machine learning, because you have 3 classifications. There's 3 species, Setosa, Virginica, and versicolor. Okay, you have 3 species, and then and the input data is all numeric, and it's very clean. Okay, often in real life, your data sets are a lot more messy, and don't are not as nice. Okay, so anyway, when I load this up, we can take a look at the different keys in there. All right, and so you have the data and the target. Okay, so if we just kind of take a look at the first 10 rows of the data, it's just this big matrix. Okay, there's actually 150 rows in the data. Okay, 150 rows, 4 columns, and so you have kind of this n by 4 matrix. Each column represents, one of these variables: sepal length, sepal width, and petal length, petal width, things like that. Okay, and so you can get the names of the features, and so you have, sepal length, sepal width, petal width. Those are all listed, and so those would be the column headings there. The targets would be the classification. Okay, and so right now the targets are just stored as integers, class 0, class 1, and class 2. And if you want the names of those targets, you have Setosa, versicolor, and Virginica, those being the different species of iris. Okay, and then there's also, you can also ask for the description of the iris data set, and it kind of gives you all of these things, and it also, whatever, all of this this information you get. Each of the 3 classes are equally distributed, and the data all shows up in here. Okay. All right, and so what we're going to do, first I'm going to do a train test split. Okay, so we talked about that, and so what I'm going to do is I'm going to just kind of pull off around 20%. So 20% out of 150, we're going to take off 30 observations, okay, and put that into our test set. And then the other 120 will be our training set. Okay, and we're also going to stratify based on the classification labels. Okay, so if I did it totally at random, when we do it, the test set might end up having, you know, more Setosa and fewer Virginica or something like that. But here I'm going to stratify on this on the species variable, and that will kind of ensure that all 3 species are equally represented in the training set and will be equally represented in the test set. Okay, so I'll take iris data and iris target, both of those things, and we're going to split them. The iris data will get split into X train, X test. Iris target will get split into Y train, Y test. All right, and then for reproducibility, I'm going to set random state equal to 1. And we'll go ahead and do that. Okay, and so now I can ask, what's the shape of my training set? And now I have 120 rows, 4 columns instead of 150 rows. And then I can ask for, you know, how many of each observation shows up in, or of each category show up in Y test. And it says you get 10 of each. Okay, so this just shows that, you know, the stratify statement indeed did it. Okay, all right, and so now we can go ahead and start fitting a couple different classification models, right? So if you just type in sklearn, there's different kind of classification things that we can do, right? And so we'll take a look at the nearest neighbors today, and we'll also look at naive Bayes. But certainly you can fit a bunch of these other things as well. Okay, so what we're going to go ahead and do is we'll fit the K nearest neighbors classifier, right? And the way the K nearest neighbors classifier will work, okay, is here is my data set. What we're going to do is we're going to take some observation, all right? So let me just kind of zoom in here, right? And so this is our kind of our training data, and we've got kind of the 3 different species represented in red, green, and blue. And so let's say we have an observation that shows up, say, right here, okay? Right here. And then we would say, okay, if an observation shows up right here, how should we classify it? We're going to count, okay, what's the nearest neighbor? Okay, to this thing, probably the nearest neighbor is this red dot. So the 1 nearest neighbor is red. And so if we put it right here and use 1 nearest neighbor, it would get classified as red. If we said the 3 nearest neighbors, it would probably be this red dot and these 2 green dots. And so now in this vicinity, the 3 nearest neighbors are red and 2 green. And so each dot gets a vote. And we would say, okay, the 3 nearest neighbors are 1 red, 2 green. So the 2 greens vote, and we would classify it as green, okay? And you know, if we said 5 nearest neighbors, we would say, what are the 5 nearest observations? And it's probably going to be these 5 points right here, okay? And then again, out of those 5 points, 3 of them are green, so the dot would get classified as green, okay? Whereas if, you know, we put a dot over here in this corner, if there's some new observation that shows up in this corner, we say, what's the nearest neighbor? Nearest neighbor would be this blue dot, so it would get classified as blue. We say, what are the 3 nearest neighbors? Okay, if we put a dot in this corner, the 3 nearest neighbors would be these 3 dots. And so all 3 are blue, and so it would get classified as blue. And you know, as you draw more and more, a larger and larger circle, probably blue is still going to be dominant, right? If you put a dot in this corner, the nearest neighbors would all be red, you know, and just kind of depending on where you go, you know, you're going to kind of draw a circle and say, you know, what are the closest nearest dots, okay, nearest observations, okay? The example I've shown you is just this two-dimensional example, but the thing is this can be applied in higher dimensional data. And so you can kind of imagine the dots being plotted in 3-dimensional space. and you say who's in the nearest neighborhood, and now your neighborhood is in this three-dimensional sphere. Okay, and then you could also imagine, it's hard to picture, but you could also imagine plotting the dots. Here we have 4 variables, and we could plot the dots in a 4-dimensional space, and given a new test location, we say what are the closest observations in this 4-dimensional space. And again, kind of the idea being you look at the classifications of the observations in kind of that nearest sphere of influence, and the ones that the most observed class is going to be the most probable class for this new test observation. Right. So anyway, just to kind of give us a sense of the data, we can do we can use Seabourn and matplotlib, and I can just do a Seabourn pair plot. Okay, so here's first I'm going to append the species information, okay, using ytrain to my xtrain, and if we take a look at that, we can see we've got our 4 variables up here, and then the species classification, and then I'm going to go ahead and create a pair plot. Okay, and so Seabourn automatically colors this, and I think this is pretty much the exact same plot that we see here, just using slightly different colors. So if you look at kind of sepal width here, you get the same plot that we have here, except, and then here we have histograms. So basically what shows up on this Wikipedia page also shows up right here as a pair plot made by Seabourn. I probably could have done the data column names to be the feature names, but that's okay. All right, so so this is what we have, and basically we're going to try to do a K-neighbors classifier. All right, before I get to that, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is E. E as in elephant. E as in elephant. Is your first view quiz answer. Okay, so the K-neighbors classifier is found under sklearn neighbors. Okay, and again, if you're not quite sure, because there's so many things, you basically just go to the scikit-learn documentation and you say, what's the model that I kind of want to try out? And you say, all right, I kind of want to do a nearest neighbors classification. And you click that, and then you can kind of see there will be some examples, nearest neighbors classification. And so you can click this, and this will have the code that they used to do it. Okay, and kind of the important thing here to learn is we want to do sklearn from neighbors. So the term is sklearn.neighbors.kneighbors classifier. You can also kind of click any of these things, right? So all of these things, you can click the documentation and it will give you the reference. So here it says the name of the function is sklearn.neighbors.kneighbors classifier. And so depending on how you read the example, there's a few ways you can do this, right? So one is you can do from sklearn import neighbors, and then you call neighbors.kneighbors classifier. Or you can also, the way I've written it in my code is I've written from sklearn.neighbors import kneighbors classifier, and then I just call kneighbors classifier without reading it in this way. So you can call it in as neighbors.kneighbors classifier. You can also just call sklearn.neighbors.kneighbors classifier. You can do import sklearn and then do sklearn.neighbors.kneighbors classifier. That's another way to do it. But here I'm just saying from neighbors here. Okay. And then when you set up the model, when you read it, okay, the default is using 5 neighbors. So actually I could have set this up without anything, but you can also provide different arguments, right? And so uniform is uniform weights, meaning all the points in whatever neighborhood you have will be weighted equally, but you can also change this to say the weights will be based on distance or some other function that you provide, okay? And so you'll say, so if you say the weights are based on distance, then the observations that are closer, so right, you might say, let's look at the 5 nearest neighborhood, the 5 neighbors in the 5 nearest neighbors. So you have some observation, you say, what are the 5 nearest points? And the nearest points will get kind of weighted based on the distance to your test case, based on their based on that, right? There's a few other ways that can be used to compute the nearest neighbors, and a few different options and arguments that you can use, and you can always read the documentation for more details. But the basic is you can just specify the number of neighbors here. Okay. All right, and when you do that, that establishes your K-neighbors classifier. So here I've got K and N. I set that up, and this is just going to be a K-neighbors classifier. And then what we're going to do is we're going to train it by providing the X matrix, the input matrix, and the target values, which are shown up in Y. So I've got the X train and Y train. So we'll go ahead and fit that. And then now that we fit the model, okay, we can now make predictions for our test observations. Okay, so we're going to do knn.predict on X test. Okay, and so these are the answers that it predicted for the 30 observations in our test set. Okay, and then we're going to compare this to the actual values. Okay, and so the actual labels are these. Okay, and so we can say, all right, did anything get misclassified? Right, and so we can say, all right, this one, our prediction predicted 1 and the actual value was 2. But looking at everything else, I'm not detecting anything. Okay. All right. And so what you can do is you can create what's called a confusion matrix. Okay. And this is one way to kind of measure how well your model performed. So this is going to be from sklearn.metrics. sklearn.metrics import confusion matrix. And again, I point you to the reference. Okay. So under metrics and scoring, quantify the quality of the predictions. So let's find the confusion matrix. All right, so you can click the confusion matrix for kind of its reference on how to use it. And what we're going to do is we're going to compare the true values versus the predicted values. Okay, as those are the arguments that you use to specify that. So here the true values are the values in Y test. We're going to compare that to the predicted values, which are found using our model.predict X test. Okay. All right, and so this is the confusion matrix, and basically what we want to see is a diagonal matrix. A diagonal matrix means everything got classified correctly. And what we have here is that, one time the true answer was 2. Okay, so that's this row. The rows are basically the true answers. So true answer 0, true answer 1, true answer 2. And one time when the true answer was 2, we predicted a 1, and then the other 9 times we predicted 2. Okay, and so that's what we have right here. Okay, if I were to change my neighbor classifier, and let's say I used nearest neighbors, just the one nearest neighbor. Okay, we could see how well it performs, and it actually gives me the same performance on our data set. Okay, I could try another model using the 25 nearest neighbors, which is a little bit silly. Okay, and we can see how well it performs. And so if I use the 25 nearest neighbors, we get slightly worse performance, where we made 2 misclassifications. Okay, and so so this is what you have. And so you might say, okay, how should we go about picking how many neighbors that we have? And so you could go through this and you could say, you know what, I want to try fitting a k-neighbors classifier where the number of neighbors is 5. I want to try it out where the number of neighbors is 1. I want to try it out where the number of neighbors is 25. And you could keep redoing this and you just basically fit it to your data. You make predictions and you take a look at its performance. Okay. There's another function called grid search CV. Okay. And what grid search CV is, it will perform what's known as a grid search, which is basically you give it a kind of a vector of values to try out. And if you have like multiple parameters, so in some parameters, so in some models, maybe you have like a gamma and a lambda and an n, different values to try out. You can say, I want you to try out 10 different values for lambda. I want you to try out 5 different values for gamma. And it's going to do basically all 10 values of lambda for every value of gamma. So it's going to try out basically 50 different combinations, and it will report back its performance after every single combination. Okay. And so depending on how many parameters you're searching for and how many values of each parameter, your grid search can end up being very, very big. Okay. But here we're going to just mess with one parameter, the number of neighbors, and we'll just try out a bunch of different values. Okay. So so this is how it's going to work. Okay. So we're going to do actually we'll try out two different parameters. Okay. So we'll do model selection. So this is sklearn model selection, and we'll use grid search CV. Okay. In grid search CV, we'll do cross validation. Okay. And it's going to kind of measure its performance this way. All right. So we're going to give it, we're going to say try out neighbors 1 through 50. Okay. Try out anywhere from using 1 to, I guess, 49 neighbors, or 1 through 50 neighbors. And then also try out the uniform or the distance-based weights. Okay. So this establishes our parameter grid. Okay. And so the parameter grid is going to be a dictionary, and the values inside the dictionary, the keys for our dictionary will be the arguments that get used, right? So here the argument is n neighbors. So we want to try n neighbors taking on values anywhere from 1 through 50. And then the other argument in the k-neighbors classifier is weights. Okay. So the keys that I'm using here have to kind of match up, right? If I left out the underscore here, it's not going to work. So the parameter grid is going to be this. We're going to establish just a k-neighbors classifier that has no arguments in it. Okay. And then we're going to call grid search CV, grid search cross validation, on this new k-neighbors classifier. We're going to provide it the parameter grid, which is a dictionary of all the kind of parameters that we want to try out. And we're going to say do kind of 5-fold cross validation. Okay. And here we're only just using the training data. Okay, so we'll go ahead and try that out. And when we do this, this is we say fit this model on all of our training data. Okay, and tried it out. Okay, it tried number of neighbors anywhere from 1 through 49, and it tried out weight, uniform, and distance-based weights. All right. So what was the best performing parameters? Okay, best performing parameters was using 13 neighbors and uniform weights. All right, and then we could say, what was your accuracy score? And said when you use this, we got an accuracy of 0.9833. Okay, so let's just go ahead and see how well it performed. And so when we look at the training data, it made 2 mistakes in the training data using 13 nearest neighbors. And so its accuracy is 0.9833, 118 out of 120 things in our thing. And that's where this cross-validation score is coming from. Okay, so we can say, all right, how well does this perform on the test data? how we get the same performance as we did before. But Grid Search CV did try out all of the different things, and this is what it determined to be the kind of the best performance as far as the training data that we gave it. Okay. You can see also just kind of get a cross-validation score, see if that gives us anything different. And so we can establish a, using Neighbors Classifier, using 13 nearest neighbors. And we can also ask for kind of its cross-validation score. And basically, it's getting 0.9833, which is the average of this. And, when you do cross-validation is equal to 5 out of 120 observations, each fold is going to have divided by 5. Each set's going to have 24 observations. So out of the 5 folds, in 3 of them it got all everything correct, and in one of the folds, or in 2 of the folds, it got 1 wrong. 1 out of 24. So I think 23 out of 24 is that number, 0.95833. Okay, and so that's where these numbers are coming from as far as the cross-validation goes. Okay, so Grid Search CV, although I think because our data set is kind of is what it is, that the we didn't really get to see how Grid Search CV will really optimize performance over a bunch of different options here. But it is a handy feature to be able to kind of search over several different possible models to use, especially if you have some kind of meta parameter that you need to establish, how many neighbors to use, how many clusters to search for, and things like that. Okay, let me go ahead and give you your second view quiz answer. Today's second view quiz answer is C. C as in cat. C as in cat. Okay, and then the last thing I want to show you is the Gaussian naive Bayes classifier. Okay, so the naive Bayes classifier uses Bayes' rule to calculate probabilities that an observation belongs in a class here. Okay, and so if you remember Bayes' rule, where the probability of A given B equal to the probability of B given A times the probability of A divided by the probability of B. Okay, and basically what we want to say is we have some vector x, which will consist of 4 values, right? Maybe 4.1. Let's take a look at one of our. Okay, let's do this. 5.1. You have these 5.1, 3.7, 1.5, 0.4. Okay, and so what we want to know is what's the probability that the plant is Setosa. Those are the species. Setosa, given that x is equal to 5.1, 3.7, 1.5, 0.4. Okay, we also want to figure out what's the probability that it's versicolor. That's another species, given x value equal to those things, versus what's the probability that it's virginica. Sorry that my thing is lopsided here. ... Okay, so given those values, okay, and so basically any of these things is going to be, well, what's the probability that x is equal to these values, 5.1, et cetera, et cetera, et cetera, given, so we're just flipping this, given that it came from Setosa. Okay, and we're going to multiply by the probability of Setosa. divided by the probability of X taking on these values. Okay. And so this part right here, this is the likelihood. Right. So all I'm doing is I'm just applying Bayes' rule, which says if you want to swap A and B here, if you want to find the probability, if you want to find the probability of A given B, you can find it by doing the probability of B given A. So in our case, we want to know what's the probability that it's Setosa, given that we have these measurements. And it just says, well, figure out what's the probability of getting those measurements if it came from Setosa, okay? And then you also have to kind of multiply by the probability of Setosa, divide by the probability of B, et cetera, et cetera. So this part, so we want to say, okay, well, what is the probability that X is going to equal this vector, 5.1, 3.7, 1.5, 0.4, given that it came from Setosa, okay? And this is where the naive Bayes comes from, okay? So naive Bayes, the naive part, says, you know what, we can factor this, all right? So what's the probability that, sepal length equals 5.1, given that it came from Setosa, multiplied by what's the probability that sepal width equals 3.7, given that it came from Setosa. So we're going to just factor it, okay? Naive Bayes basically means all variables are independent. And can be factored. So normally there's some kind of joint distribution, right? And so we're going to say, what's the probability that, petal length is 1.5 given Setosa, and probability that petal width is equal to 0.4, given that it comes from Setosa. Okay, so so the naive Bayes says we can do this. We can take this joint distribution of 4 variables. So having a joint distribution of 4 variables is going to get factored out into kind of the product of 4 different distributions multiplied together. So we have a question. It says, when you do a cross-validation using cross-val score, do you only provide X-train and Y-train? Yeah, so cross-validation is only going to be done using the training data. And if you want, and then you use the test set only kind of after you use, so cross-validation's intention is that you basically just use it only on the training data, and you're kind of splitting up your data into kind of different validation sets. You can use your test set later on as another kind of metric after the fact, after you've established all of like which model to use. Okay, but going back here, this is what we have. All right, and so what's the probability of sepal length equal to 5.1? So the Gaussian naive Bayes is basically going to say that, sepal length comes from a normal distribution where the mean is equal to basically the mean sepal length of the data and the standard deviation is equal to the standard deviation of sepal length in the data. Okay, I guess I should say of data for Setosa, okay, for Setosa. Okay, and so you're going to have a whole bunch of these distributions. You're going to actually have 12 different normal distributions. You're going to have sepal length for Setosa you'll have sepal length for versicolor, and you'll have sepal length for virginica. Okay, and then you'll also have sepal width for each of the 3 species, and then you'll have petal length for each of the 3 species and petal width for each of the 3 species. And each of these are going to be estimated as normal distributions, and you're going to use the mean of the sepal length or sepal width or petal length or petal width for all of the observations that fit a certain class. Okay, and so you can do this in a manual sense, but the Gaussian naive Bayes will also kind of do this for you. Does that kind of make sense as far as what the naive Bayes classifier is doing? All right, so all we have to do is we just call Gaussian naive Bayes. This comes from sklearn naive Bayes, okay? And just again, using the naive Bayes, we'll use the Gaussian naive Bayes, but there's several different kind of things if you want to, depending on what kind of variables you have. Okay, so here's the thing. We're going to use the Gaussian naive Bayes here, and then we're just going to, again, once you have it, you're going to fit between your training and your on your training data, and then we'll ask for predictions on the test cases, and this is what it has. We'll see how it performed, and it's also still making one kind of mistake there. We can see kind of its cross-validation performance, which is just okay here. It's 95% accurate on the training data here. So when using the training data, at least for our current train test split, the naive Bayes classifier is only achieving 95%. Yes. Okay. And then, all right. And okay, so that's it. That's all I have here. These are just kind of some basic tools. And so you can see, as far as using sklearn, there's not a ton of like output. There's not a whole lot to see, right? You just, the calling, the establishing of each kind of model and the fitting of the model, it's all done in just like 1 or 2 lines, and it just kind of spits out your predictions here. Okay, and so kind of getting used to how sklearn inputs and outputs your things. There's not like a ton of diagnostics and things. Will take a bit of getting used to. Okay, I strongly encourage anytime you want to try something out, start at the sklearn scikit-learn documentation, and read the examples, and see if there's any kind of other examples or pictures that might show you what it is that you want to achieve. Okay, that would be kind of your best reference to get started, and I think that's probably your best way to just kind of try things out there. Okay, let's call it a day there. Let me give you your last view quiz answer for today. Today's view quiz answer, the last one is D. D as in dog. D as in dog. That's your last view quiz answer. Okay, we'll end there, and we'll see you guys on Friday. Have a good evening. And once again, the homework 5 deadline is extended till Monday. I'm going to cancel homework 6, and that will be that. And then don't forget to just do earn 1,000 XP on data camp sometime this week. Okay, have a good night. We'll see you guys on Friday.